So dimensional analysis is a really powerful tool for investigating physical systems. The dimensions give you the scale of the system, and the dimensionless parameters, when you combine your parameters into dimensionless quantities, you get the behavior of your system. Now the nice thing is that you have less dimensionless quantities than you have dimensional ones. And indeed the Bucky and Pi theorem has just told us that for every fundamental physical dimension we have in our system, we can reduce our number of parameters by 1. Let's do an example of that from quantum mechanics. So the time evolution of any quantum state is given by the Schrödinger equation and the Hamiltonian. If we put that into the position basis and we have something like a harmonic oscillator, then we'll get a differential equation for our coefficients in the position basis, which we often think of as our wave function, that looks like this. Now this is just a partial differential equation that depends on h bar and m and omega, and as we change those parameters we're going to get different solutions to that equation. But we also know that if we put it into dimensionless form, then we're going to have it depending on less parameters. And so I'm going to pick some time scale. So tau is going to be dimensionless, not dimensionful. So it's going to be proportional to t, but we're going to divide it by some time scale. And r is going to be dimensionless, and it's going to be proportional to x, but again divided by some length scale, x naught. So now we're going to convert this equation of motion into those parameters. We know from the chain rule that this derivative with respect to time can be turned into a derivative with respect to tau. I can tell I got that right because this had time dimensions on the bottom and this has time dimensions on the bottom, so that's fine. And so forth with this. We can go to dr squared, and I know I need a 1 on x naught squared to get my units right, and indeed if I check my chain rule that's what it will be. Now we can group these things. If I multiply both sides by t naught and divide by h bar, I can push this part down to something that's purely dimensionless. And so now every other term is going to have to be purely dimensionless. So these objects here, this big cluster of things and this big cluster of things, must be dimensionless. So I can make them equal to anything I like. For example, I could make them equal to 1. If I was trying to make this equal to 1, then I'd have to set, then that would be 1. And if I plug that into here and I want to set all of this to 1, then I would have, so by judicious choice of x naught and t naught, and this t naught, if we plug it in, by the way, we're going to get 2 on omega, which is fairly obviously a time scale, a natural time scale of the system. So by judicious choice of t naught and x naught, we've managed to make this equation very simple indeed. What's important about that? Well, first of all, we don't have an h bar, an m, and an omega. It was kind of obvious from the start that the only thing that mattered for this term wasn't h bar by itself, but h bar squared on m. And so there was no need to change those independently. Well, it turns out there's no need to change anything at all. Bucky and Pi told us that with kilograms, meters, and seconds, we could get rid of 3 of our parameters, and we only had 3 parameters, and so our final equation depends on no free parameters at all. So this equation here, which has no free parameters, I can just plug in an initial condition and fire it off, and I know what this equation does. If I analyze this equation, I am done. The only thing I would ever do if I changed my physical parameters here is I would relabel my axes. Now what if we were to add an extra term? Supposing we were to add plus k to the 4th x to the 4th in our potential there. Then of course this would give us a new parameter, and down in here we would end up with an extra term. And this here would be a dimensionless parameter. Let's call it alpha, and we don't have any extra dimensions, so we can't reduce our problem anymore. And so now if I knew all the different behaviors of this equation for different values of alpha, I would in fact know all the possible ways that this equation can be solved. And so it's really powerful to take our equations of motion to dimensionless equations, and we can figure out exactly how a system behaves. And then of course when we want to talk about our physical systems, we just put our length scales and our time scales and whatever other scales we have back in, and we've got our full solution of the problem.